2.4 is on. It is the derivative. We've got enough of a basis now. We can finally define the derivative and make some progress here in this section and in some coming sections. Okay, let's begin with this statement right here. Try and see if I can fit all that on the screen. Okay, let me hit my focus, get a little bit better. Perfect. Okay, we want to know the instantaneous rate of change for f of x at x equals a. And so if you remember back from the what is calculus couple videos I did to start the semester off, I think I called it what is math 121. You saw this image here. Okay, so if we have the graph of a function, could be anything, and let's say we'd like to know the instantaneous rate of change at some moment a. So we got our point on the graph there. The instantaneous rate of change is the slope of what we refer to as the tangent line. So a tangent line, it's kind of tricky to define, but essentially it's the line that moves in the same direction as the function is at that moment. So here the function is kind of going up and curving, so the tangent line will come and it'll just skim by, and the tangent line in this case will only touch that point right, it'll only touch the curve at that one point, and then it will just graze by and keep going off in the same direction. So that's the tangent line, and what we are really curious about is the slope of that line. That will tell us how fast is our function increasing at that one instant. So it's the instantaneous rate of change. Okay. We're going to have to build up to this, and obviously we're going to be using limits and that sort of thing. Okay. Let's go back a little bit and look at this from a simpler point of view. We're going to start with the average rate of change between 2 points from x equals a to x equals b. So I've got a similar drawing, okay, but now we haven't just marked off one location, we've got two, at a and at b, and we're just going to draw the line between those 2 points. Okay. If we wanted to know the average rate of change from one moment to the next, we could find the slope of this line. We refer to that line as a secant line. Now these names are kind of funny. Tangent line, we use that word tangent in day-to-day language. Hey, sorry I went off on a tangent there. Kind of has the same, it really has the same meaning as a tangent line graph. If you go off on a tangent, you kind of like, go off separately from the mainstream of thought for a moment, but there's a connection, all right? So secant, we don't really hear that word ever except in math, at least I don't. But that's what you call a line like this, connecting 2 points, 2 separate points on a curve, is a secant line. Okay. All right. Let's take a look at this. How would you find the slope of that secant line? Well, hey, we know the formula for slope, right? M equals, let me write it over here, m equals y2 minus y1 over x2 minus x1. So going way back in our algebra, that was beginning algebra, we learned the formula for slope. So if we were thinking of it as a function and the points a and b, then you could say this right here. So think of, y2 is the y value there. Well, that's f of b. Right? y1 is f of a, the function value at a, over x2 would be the b, x1 is the a over b minus a. And it's that exact formula, but written a little bit differently, kind of in a function sort of form with a and b. Okay. Let's pause on this idea of the average rate of change. We're going to do an example. All right, here we go. Let me read you the prompt here. Says a ball is dropped and will fall according to this function. F of x equals 16x squared, where x is seconds and f of x is feet. Okay, so the ball is, you're just someone standing very high up, and they just drop the ball. They don't throw it or anything, they just release the ball, and it begins falling down towards the ground far, far below. And so this function would tell us how many feet it has fallen at any given number of seconds. Okay, so after 1 second, we could say, well, it's fallen 16 feet, that sort of thing. Now, when it comes to objects falling, do objects fall at the same speed? Are they going the same speed the whole way? No. Gravity, they're accelerating towards the ground. So if you fall for 1 second, that's actually a pretty significant fall if you fell for an entire second. But that'd be nothing compared to falling for 10 seconds. Right? That would be really bad. If you're a ball, it's probably okay. Okay, so what's the question? Find the average velocity from x equals 3 to x equals 4 seconds. So we know, it's changing velocity as it's falling. And so we're building up to that, right? The speed at any instant. But we're going to start, what's the average velocity between 3 and 4 seconds? Okay. Well, we're just going to use our formula right there, right? It's the slope of a secant line, which is really just, the same old slope formula we've been using. So think of this as A and this as B. And I think I'm coming to the end of my page, so I just squeezed in all the work right there. So we're going to label this as V average, average velocity. Not uncommon to see that sort of notation. Okay. And there we go, f of B minus f of A over B minus A, just plugging in the 4 for B, the 3 for A. And then my next line is right over here. And at this point, I'm plugging those numbers for the function values just right in there. So 16 times 4 squared would give you 256. 16 times 3 squared would give you the 144. And it's over 4 minus 3. And so then simplifying, well, if you 256 minus 144 would give you 112 over 1, so 112. The average velocity is 112 feet per second. And that is really moving fast. So you kind of think for a second, well, if the average velocity between 3 and 4 seconds is 112 feet per second, then it's going to be going a little bit slower at 3 seconds, right? And it would be going a little bit faster at 4 seconds. And 112 would be just kind of somewhere in between those two. Okay. Sounds reasonable. I went ahead and just sketched a graph of what we just did, just to kind of give you a little bit more detail here. So f of x equals 16x squared. Well, it's a parabola, right? And it passes through. It's got a vertex at the origin. It's that. Now, the truth is this parabola is actually very, very narrow, very steep because of the 16. But that's okay. We don't have to go that far. And then 3 seconds to 4 seconds. Right, there's the point at 3, there's the point at 4, and we draw that secant line. Now, actually, this would be very, very steep because this curve would be so narrow. But just for a sketch, I think this is better. And so the secant line has a slope equal to 112, that line right there. 112 over 1, right? Rise over run. But if you look at each individual moment, like 3 seconds, well, if you were to draw the tangent line there, it would not quite be as steep as our secant line, right? Or if you were to draw the tangent line at 4, it would be more steep than our secant line. So the secant line, it's our average, right? Somewhere in the middle of those. Okay. Now let's take it a step further. take it a step towards getting the instantaneous rate of change at some place. Check this out. So I'm just gonna not think of this as a 4 anymore. I'm gonna put a variable there. Okay. And you know what? I think I'm going to keep correcting my own notes live on camera, and I think that's okay. Because if I was lecturing in class, sometimes I make adjustments live and nobody knows. The only difference here is everybody knows. So here's what I'm going to do. Instead of putting a 4, I'm going to say this is 3 plus h. So I'm still going to put a point above 3, and I'm going to put another point above 3 plus h. And then I'm going to draw the line between those. Luckily, I have a ruler right here. So I'm going to draw that secant line. Okay. And now here's what I want you to picture. I want you to picture the gap between these two shrinking. I want you to picture this shrinking back towards 3. Okay. We're going to attempt to get the tangent line. That's my drawing of a tangent line at 3. That tangent line is supposed to be coming right down here and grazing past that parabola, just touching it there at 3. How can we use our knowledge of the secant line to obtain the tangent line? And of course, the hint is written plainly right over here. If we want to draw, this point back towards 3, what would that do? So as the points got closer and closer together, if this point moved back a little bit and then I drew a new secant line, I won't attempt it because I think it would just get too messy. But if I was to move this back a little bit, maybe halfway, actually let's do it. If I was to shift this back and then draw another line directly above on the parabola and then draw that, so I still have a secant line, but now the slope is a little bit less. And I could do it again, right? I could draw that back halfway again. And now connect these. And what's happening every time I draw this back a little bit? That slope is bending down, and eventually, as it hones in on 3, that slope is going to be exactly this tangent line. The tangent line is the lowest one of all of them. And hopefully you follow my logic there as we start to draw this second point back towards the first one and keep drawing secant lines. Those secant lines look more and more like the tangent line. And eventually, when we get infinitely close to 3, we will have the tangent line exactly. So the idea is as h approaches 0, right, as this value that we're adding gets smaller and smaller, as h approaches 0, the secant line approaches the tangent line. Okay. So what does that mean as far as our calculations go? So it turns out we can take that same formula that we have for the slope of the secant line and simply apply a limit as h approaches 0, and that will, in the end, get us the tangent line. Here's what I mean. Find the instantaneous velocity at x equals 3. Okay, let me keep this drawing here. Now we're going to go for it. We're going to get exactly, precisely how fast this ball is falling at the 3-second mark. Okay, here's how we're going to do it. Let me erase this just for simplicity's sake for the moment. Here's our slope between 3 and 3 plus h. Okay, so think of 3 as the a and 3 plus h as the b. So it would be f of 3 plus h minus f of 3 over 3 plus h minus 3. F of b minus f of a over b minus a. Okay. Instead of 3 and 4, now we're going with 3 and 3 plus h. So that would get us the slope of the secant line. But now if we want to turn it into the slope of the tangent line in the front, we say, okay, then throw on a limit as h approaches 0. So that value there, these 2 points are going to get closer together. This is going to get pulled back towards the 3. Oh man, this is exciting. Let's see how this plays out. We're still using the same function. It is still f of x equals 16x squared. Same function as before. Okay, so let's check it out. It's going to take some work. There's quite a bit of algebra going on here. So what is f of 3 plus h? Well, we'll put the 3 plus h in for the x, right? 16 3 plus h squared minus 16 times 3 squared. Now that's the same as it was in part A. And then it's over. I'm just going to leave this for the moment, 3 plus h minus 3. Okay. Now it's going to be our job to multiply all this out. Obviously, we can do that calculation as well. So we've still got velocity. Notice we don't say v average anymore because it's instantaneous. So we just say v for velocity. So v equals, I'm still copying limit as h approaches 0. I'm just doing the algebra over here. So let's see, if we FOIL this, we've got 9 plus 6h plus h squared. Doing that calculation, we get the 144 again. And you'll notice in the denominator, 3 minus 3 cancels nicely, and we just get the h. Okay, let's keep going. There's still some nice cancellation in the numerator. 16 times 9 is 144, and then you would subtract the other 144. And then 16 times 6h gives you 96h. 16 times h squared, 16h squared, and it's still over h. Okay. Now maybe this is kind of looking familiar. It's like those difference quotient problems that we were doing in the review and you had a quiz problem on it. Okay, yes, there's a big connection there. Okay, now at this point, we can cancel an h from each of the terms. You could also think of factoring an h out from the numerator. I kind of like to think of it that way, and then they cancel. So our next step will be v equals the limit as h approaches 0. Notice we're just copying that the whole time. Now the simplified version, 16 plus 16h. And at this point, finally, we can plug in that 0. And, well, 16 times 0 is gone. The velocity equals 96. And, of course, the units here are feet per second. That is exactly how fast the ball is falling after 3 seconds, or at the 3-second instant or moment, or the 3-second mark. That is pretty amazing. Okay, we'll stop this video here. You know what? Just one thing I want to point out. So we noticed the connection between this and the difference quotient. That's big. Also, just thinking about limits. What did we do? If you were to plug in 0 right away, what would happen? Well, it'd be f of 3 minus f of 3 over 3 minus 3. It'd be 0 over 0, right? If you tried to plug it in right away. You can't do that. We don't have an answer. Or maybe we should say there is an answer. That's just not the way we can get it. It reveals there's a hole. So as this moment draws back to the same point, if we draw it back to equal the same point, then we're going to get something that we can't determine, right? 0 over 0. But if we do it as a limit, we can work through all this and get a number in the end. We have found a way to find 0 over 0. We have found a way to find the slope at the same point. Isn't that incredible? Okay, really, really cool. Let's stop this video here.